Okay, this is 6.3, and this actually should say similar triangles, not similar polygons. And students will be able to identify similar figures and solve problems involving scale factors. Okay, discussion question. Well, in the class I'm going to ask you guys to recall, why could we not prove triangles congruent using AAA? And if you remember, we said that triangles can't be congruent by AAA because we can have two triangles with the same angles, but they could be different sizes. Well, when we're talking about similar triangles, size doesn't matter. So we can maybe use AAA or something like it. So what I want you to do is complete these two triangles. I've got the angles here for you. I got angles D and E and R and S, and these are actually the same things, same angles. I just spread one out a little bit bigger. So D is congruent to R, and E is congruent to S. E and S are the same measure of angles. And F is going to be some point up here, and T is going to be some point up here where the triangles come together. So what I want you to do is, on your paper, actually complete these drawings. Now, obviously, mine isn't going to look that good because I'm doing it on an iPad, but I want you to complete it something like that. Use a ruler and make it nice and neat and complete it so it looks something like that. And then I want you to measure all of the sides. Measure DE, DF, FE, RS, RT, TS in centimeters. Do it in centimeters. And I want you to compare the ratios that you get. So you're going to take the distance of DE and you're going to put it over RS. And you're going to take the distance of DF and put it over RT. And the distance of FE and put it over TS and see what you get. So I'll give you some time to do that, and then you could just pause the video and come back to me. Okay, well, when I did it on paper, here's the measurements I got in centimeters. I got 1, I got 2.4, 3. And over here I got about 1.8, 4.5, and 5.6. And so when I made my ratios, I got a 3 over 5.6, I got a 1 over 1.8, and I got a 2.4 over 4.5. Now, remember, these aren't going to be exact because obviously they could be a little bit more or less than whatever my measurements were, but they give us a pretty good estimate. And sure enough, we find 3 over 5.6. Well, this is about 0.5, I'd say about 0.54 when you round to the second decimal. 1 over 1.8, this is 0.55. And 2.4 over 4.5, this is 0.55. So we see these are all pretty close, and they actually should be exactly equal, but there's a little bit of human error in our measuring. But other than that, we do find that they are actually equal, and so these triangles are definitely similar. And remember, we didn't start with 3 angles congruent. We only started with 2 angles congruent. 2 angles congruent. That's it. And the sides had some proportion, but we didn't know what that was yet. So all we had was 2 angles congruent. That's all I started with. And with those 2 angles congruent, we were able to prove, once we completed the drawings, that the 2 triangles were similar. Well, that's important, because that's what postulate 6.1 is based on. It says that if 2 angles of one triangle are congruent to 2 angles of another triangle, then the triangles are similar. That's all we need is 2 angles. If we just have 2 angles congruent, then we know triangles are similar. So for example, since D is congruent to R and E is congruent to S, we can say the triangle DEF is similar to triangle RST. And we still want our corresponding parts to line up. So D should be, angle D should be congruent to R, angle E should be congruent to S, and it ends up that angle F is congruent to T. Okay, so that's postulate 6.1, or angle-angle similarity. Theorem 6.1 is this. It says if the measures of three sides of two triangles are proportional, then the triangles are similar. For example, we found out that all of these proportions were equal, or approximately equal, right? I mean, that was just because of human error, but if we were to actually get this out, measure it in millimeters, and there was no variance because of the thickness of the lines, right? And we could do it very exactly, we would find out that they are exactly equal. And so since that is the case, that's enough information to show that DEF is similar to triangle RST. And normally you would write it like this, triangle DEF, all in one line, but it's kind of hard to write small. Okay. So, and there's one more theorem, but that's on the next page, so let's go there. Okay. Theorem 6.2 is the side-angle-side similarity. And it says if the measure of two sides of a triangle are proportional to the measure of two corresponding sides of another triangle, and the included angle, that just means angles in between, are congruent, then the triangles are similar. So if we were to use our example on the last page, if we knew that, hey, the proportion of DE is equal to the proportion, or DE over RS is equal to the proportion of DF over RT, and D and R are congruent because that's the angle in between both of these segments, then that would be enough to show us that triangle DEF is similar to triangle RST. And we're actually going to use this one in the example. So it says determine whether the triangles are similar. Given this little distance FG is congruent with this distance EG. And then they give us some values. They say, hey, BE here, so I'm going to draw it. BE is 15. And CF, I'll do that one in another color because it's a different triangle. CF is 20. AE is 9. And FE, or FD, or DF as they call it there, is 12. All right, that's a lot of information going on there. But you can kind of see I made the green go to this big triangle here, and I made the red go to this triangle here. Now there's one little thing that we need. Remember, in order for this theorem to work, we need to have angles in between that are congruent. Well, let's take a look at this. I'm going to zoom way into this triangle. And I want to show you, I have a little triangle inside here. And they told me that this segment is congruent to this segment. So that tells me that they are isosceles. That's a little isosceles triangle. And I know that the base angles are congruent in an isosceles triangle. So I can mark those as congruent. And now look. Now I have a side, angle, side, and then another side, congruent angle, and another side. So now we just need to see if BE is congruent to if BE is proportional to FC in the same way that AE is or proportional to DF. Okay, so we're going to do a little fraction. So we're going to do 20 over 15 and set it equal to 12 over 9. So let's see if that works. Okay, so I'm going to remember I'm putting the upper triangle or the bigger triangle on top. And I'm going to put the smaller triangle on the bottom with the corresponding sides underneath it. So you can see that BE would correspond to CF because it's like these two triangles, if they were congruent, it's like one triangle flipped around, or a mirror or reflection to this triangle because the corresponding angles are on opposite sides, the corresponding sides are on opposite sides, so that's how we get that. And we're going to see if this is in fact equal. Well, 20 over 15, that reduces down to 4/3, and 12 over 9 reduces down to 4/3. So, yes, they are actually similar because the sides are proportional and the angles in between those sides are congruent. So, we could say triangle, let's go ABE, is similar to triangle. And remember, A corresponds with D, B corresponds with C, and E corresponds with F. And so, yeah, those two triangles are similar. Okay, let's do another example here. All it says is find AE and DE. Well, let's take a look at what we know about these two triangles here. So let's zoom way in. Okay, I see that I have two triangles with vertical angles, and I also see that these two lines are parallel. So let's take a look. Well, for sure, these two angles must be congruent because they're vertical. And also, if you were to think about it, this parallel line, if it was to keep going, and this parallel line, if it was to keep going, it would look like two parallel lines cut by a transversal, which means that alternate interior angles would be congruent, because alternate interior angles of parallel lines are congruent. So I could say that these two angles are congruent. And that's enough right there to prove that they're similar, because I have two angles and two angles, but I could keep going. So I'm going to just show you one more reasons why I know that these are similar, and that's because, again, parallel lines cut by a different transversal, and so again I have alternate interior angles that are congruent. So I could say, hey, these angles are congruent as well. So that means that these guys are definitely similar. So now that I know they're similar, I just need to use corresponding parts, set up a ratio. Well, we could see that A corresponds to D and B corresponds to C, so 2 is proportional to 5, or the ratio of 2 to 5 is going to be the same ratio of x minus 1 to x plus 5, and that's how I'm going to solve this. So let's zoom out just a tad. And I know that I'm going to say 2 over 5, remember 2 is part of the smaller triangle here, is going to be equal to x minus 1 is also part of the smaller triangle, and x plus 5 is part of the bigger triangle. And there we go. I set up a proportion, and now I just solve. And solve just like I've been doing before with these types of proportions. I do the cross product. So that gives me 2 times x plus 5 being equal to 5 times x minus 1. Distribute, I get 2x plus 10, 5x minus 5. Let's see, I'm going to subtract 2x, add 5, these cancel, I get 15 equals 3x, divide by 3, x equals 5. Okay, but that's not what they wanted. They wanted me to find AE and DE. So, I know that, let's do a different color just so we can separate it. I know that AE equals x minus 1, and x is now 5, so I can say 5 minus 1, or 4. And I know that DE equals x plus 5, or 5 plus 5. And so that's 10. There we go. And that's how I do that. So, summary is, how would you define similar in your own words? Also think of at least one application of it in the real world. Alright, thank you.